Let's do a crash course in the production of ethanol, making sure that you know for the two methods, any equations, reagents, conditions, mechanisms where needed, and pros and cons for each method as well. So we'll start with the direct hydration of ethene, and the equation for this is, well, we're starting with ethene, which I'll write as, you can write it as C2H4 or CH2CH2. And then we're going to react that with water, but specifically, and we'll talk about that more when it comes to the reagents and conditions, that has to be steam. Now, that reacts in the presence of an acid catalyst, typically sulfuric acid, but could also be phosphoric acid, written over the arrow because it's not a reactant or a product. And then our product is our ethanol, which I'll write as CH3, CH2OH. Could also be written as C2H5OH. Same. This is just the more the structural formula. Now for the reagents and conditions, as mentioned before, we need steam, we need an acid catalyst, and that would typically be sulfuric acid, but could also be phosphoric acid. This also happens, and the steam is a big hint in case you forget. This is carried out at a relatively high temperature, so approximately 300 degrees, and also high pressure of approximately 60 to 70 atmospheres. Now, it's important to think about the temperature and the pressure when we start to think about any pros and cons later on. Now, when it comes to the steps, right, this is the overall equation, but this actually happens in two steps, which link nicely to our mechanism, because the sulfuric acid acting as a catalyst, which means it's going to provide an alternative reaction pathway with a lower activation energy, and it's not going to be used up itself. So it's going to be regenerated. So we can show that through our steps. Let's start with step number one. In step one, we have our ethene reacting with our sulfuric acid to give us, and I never remember the name of this, an alkyl, oh my goodness, alkyl hydrogen sulfonate, not sulfonate, alkyl hydrogen sulfate, which is where we've essentially got addition, spoiler alert, of our sulfuric acid across that carbon-carbon double bond. So we end up with CH3 CH2OSO2OH. And then in our second step, that's where our alkyl hydrogen sulfonate that we've just produced reacts with our steam to actually give us our alcohol product. And of course, because our sulfuric acid is a catalyst, the sulfuric acid is going to be regenerated at the end, which is why, again, it's not it's not included rather in our overall equation because it is not being used up. It's going to be regenerated. Now, step one, as I mentioned, as alluded to, this is your electrophilic addition mechanism that we see in our alkenes topic. Let's even write the whole name. And we see this example specifically using sulfuric acid as our electrophile. Now, for a full breakdown on the mechanism, that will have its own video. So if you want the full explanation, then you'll head over there. But for now, let's just look at the specific example with ethene and sulfuric acid. So we'll start with our ethene. We've got our carbon-carbon double bond, and then we've got, of course, our CH bonds. And then we have our sulfuric acid. Now, sulfuric acid, H2SO4, I'm going to write out as HOS and then O2OH. And I draw it like that because the structure is, I'll just do it over here next to this H2SO4. We've got our S, we've got two doubly bonded oxygens, and then two OHs. So the part that I actually care about is one of the OHs, which is why I've drawn it out like that. And then the rest of it is your OSO2OH. Okay, but just draw it out like this, or you can draw up the structure if you know it. Now, for our first curly arrow, it's going to make a lot more sense if we put our partial charges. In this OH bond, the oxygen, more electronegative, is going to be delta negative, with our H being delta positive. So our curly arrow from the pi electrons of the carbon-carbon double bond, attacking the partially positive hydrogen, and then breaking that OH bond. And what do we end up with? We end up with, of course, a carbocation intermediate where our H has now bound to one of these two carbons. Now, because this is symmetrical, it doesn't matter which carbon you put the H on. I'm going to put it on the one on the left, just because. And then that means that the other carbon is going to be the one with the positive charge. And we've also got our OSO2OH, right, which is all of the rest of this bit, now with a negative charge and a lone pair because it's taken the electrons from that OH bond. And so now our second curly arrow, of course, it only makes sense, opposites attract, will be from the middle of the lone pair on the oxygen to our positive carbon atom. And that's how we end up forming our, can I say it right this time, alkyl hydrogen sulfate. No floating bonds. Thank you very much. Alkyl hydrogen sulfate, which is our intermediate that's going to react with steam in our next step to actually give us our final product. Okay, really important that you remember essentially, or you don't forget that your mechanism for electrophilic addition can show up in this ethanol topic. So they can actually they can actually have some quite long detailed questions where they're talking about maybe the conditions of producing ethanol and then linking that with your mechanisms understanding as well. Now, considering this particular method for producing ethanol from the direct hydration of ethene, this is great for certain reasons. It's very fast. It's a continuous process with a high percentage yield and high atom economy, and also gives us ethanol, which is pretty pure. However, and let's just get rid of that. No offense. You can go down here. Um, Due to the high temperature and the high pressure, this can be really expensive to produce. And also, ethene is obtained from crude oil, right, through fractional distillation of crude oil and then cracking of those longer hydrocarbons to give us alkenes, which requires a lot of energy. And also, crude oil is a finite resource. So, there is an alternative method that does not use a finite resource, and that is the fermentation of glucose. Now, the equation for the fermentation of glucose is we'll take our glucose, which you'll hopefully be familiar with already from GCSE, photosynthesis and respiration, right? So we've got our C6H12O6. That is then going to not react with anything because this is anaerobic respiration, and this gives us ethanol and carbon dioxide. Now, for the balancing, you could go through the process of counting everything and figuring everything out, or you can remember that it's a 2 and a 2, and then you save a whole bunch of time. Okay. Now, for the reagents and conditions, again, as a reminder, this process is anaerobic respiration, which means that it is without oxygen. And in order for this reaction to take place, we do need a catalyst, but we use a biological catalyst in the form of enzymes in yeast. Right? The enzymes are what are actually catalyzing this reaction. Now, because these are enzymes, biological catalysts, and again, throwback to GCSE, these will only work, or these will work the best rather, at their optimum temperature. So we don't want the temperature to be too low because the reaction will be too slow. Didn't mean to rhyme. But we also don't want the temperature to be too high because then the enzymes will denature. So the temperature that we use is around 30-ish to 40-ish degrees because that would be the optimum temperature for our enzymes. Now, this is, I keep saying it, anaerobic respiration, which means that this must be sealed. There has to be no oxygen. So anaerobic conditions. And this is also carried out in aqueous solution. Okay. Now, as mentioned before, this is from glucose, and glucose could just come from plants. So that means that this is not coming from a finite resource like crude oil. So there are some pros. It's cheaper, we're using lower temperatures, and the glucose is from plant material, which is renewable. So we can use sugarcane, for example. However, it's a much slower process. It's a batch process, which means we can only do it in batches, right? Rather than it just being in a continuous flow. And the ethanol is of a lower purity. And so in order to purify it, we then need to carry out fractional distillation to purify, which requires, energy and time and all that stuff. Okay, so there are pros and cons, advantages and disadvantages for both methods. Important that you have a couple of pros and a couple of cons tucked up your sleeves to discuss in any discuss or evaluate type questions, and that you can write the equations and the reagents and conditions for both of your methods for producing ethanol. Make sure that you've liked this video. Leave a comment if you've got any questions. Subscribe so you see any future A-level chemistry practice questions and explanations and all my videos. And I will see you in the next one.